Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is VCM 1020 Discussions Continued, MCAT Problems from Chapter 1 and 2, and the first 3 Physics LSAs. As always, please be an attentive learner while watching this video. And as you may recall from the VCM, I promised you I would give you cleaned up solutions of the MCAT problems from chapters 1 and 2, and also clarify what the first 3 physics LSAs are. And so those are promises that I made, and this video keeps the promises. So here is the first MCAT suite of exercises. It's a biology-based problem calculating lung volume in humans. In human lungs, oxygen and carbon dioxide are exchanged in the blood within many sacs called alveoli. Alveoli, alveoli, I guess, provide a large surface area for gas exchange. Recent careful measurements show that the total number of alveoli in a typical human lung pair is about 480 million, that is times 10 to the 6th, and the average volume of a single alveolus is 4.2 times 10 to the 6th, and this is cubic micrometers. This caused some confusion before, so this is not microcubic meters, this is micrometers whole cubed. And recall that the equation for the volume of the sphere is V equals 4 over 3 pi r cubed, and the equation for the area of a sphere is, this is the surface area is equal to 4 pi r squared. So question 57 asks, what is the total volume of the gas exchanging region of the lungs? And you're given 4 answers in different units, and you have to think through which of those are the right answer. And again, these multiple choice questions like this are very common in your certification exams. This one being for admission to medical school, but this is a problem that would make sense for your certification exams as well. So it asks, what is the total volume of the gas exchanging region of the lungs? Well, the total volume is equal to the number of alveoli, which is this 480 times 10 to the 6th, times the average volume of a single one. Now, to find the average volume of a single one, you do know that this is 4.2 times 10 to the 6th, but this is micrometers, cubic micrometers. Okay, so that means we start with that. So this is the number times the volume, but then we have to change that into units that make sense here. And so we're going to change this into liters in this case to compare with that answer. And so we have this so far, but then we have to change the cubic micrometers into meters, and so that is going to be 10 to the minus 6 meters is what 1 micrometer is, and then we're cubing that, so that's this micrometers whole cubed, and so this will cancel with that, and we will have but this 10 to the 6th is being cubed, so that is 10 to the minus 18 when you're finished with that. And then I have to change this cubic meters into liters, and we know that that 1 cubic meter is 1,000 liters. And so we make that conversion, and when we do all of this, we get 2.0 liters, and the correct answer is C. And what you can see is that neither one of these two answers would be correct, nor would 120 liters. So the answer is C. Now with the same setup, we say, assuming that these are spherical in nature, that means they're like this. What is the diameter? And so you have different units. These are millimeters. All of them are millimeters, I guess. So the volume of sphere is 4/3 pi r cubed. Now note that 1 micrometer is 10 to the minus 6 meters. And if we change that to millimeters, that's 10 to the minus 3 millimeters. So we can solve for R, and then we can figure out what the volume is. So the diameter is twice the radius. So there's the 2, but then I have to take 3v over 4 pi, but then I have to take the cube root of R to solve for that. So that's going to be 3. This is 4.2 times 10 to the 6 micrometers cubed. That is cubic micrometers over 4 pi. You take the cube root of that and you multiply all this stuff together, taking the cube roots, and you end up getting 0.2 millimeters. And here you're changing it to millimeters. So the correct answer is A. Now, in the same context, we talk about individuals vary considerably in total lung volume. The people with greater lung volume can run longer and faster. And this shows the results of measuring the total lung volume and average alveolar volume in 6 individuals. And here's some data points. And you can see that this is really pretty flat. And so what can you infer about the relationship among the size, lung volume, and number of alveoli per individual as the volume of lungs increases? Well, and so here's the choices that you could infer. That the number and volume of the alveoli increase, the number of alveoli increase, and the volume of the lung decreases. The volume of the lung alveoli remains constant, and the number of alveoli increases, and both the number of alveoli and the volume of them remain constant. Well, if you look at the graph, you see there's pretty much a horizontal line, so there's no systemic upward or downward trend. Thus, the average volume of them doesn't depend on the total lung volume. It's flat. And since that's the case, the total lung volume must be equal to the average volume times the number of alveoli. So thus, as the total volume of the lungs increase, the volume of the individual alveoli remains constant, and that means that the number of alveoli increases. So the correct answer is going to be C, that the volume of the individual alveoli remain constant, but the number of alveoli increases. Now this goes into a different biology setting. This has to do with blood flow in the heart. The human circulatory system is closed. That is, the blood pumped out of the left ventricle of the heart into the arteries is constrained to a series of continuous branching vessels as it passes through the capillaries and then into the veins, and it returns to the heart. The blood in each of the heart's 4 chambers comes briefly to rest before it is ejected by contraction of the heart muscle. If the contraction of the left ventricle lasts 250 milliseconds and the speed of blood flow in the aorta, the large artery leaving the heart, is 0.8 meters per second at the end of the contraction, what is the average acceleration of a red blood cell as it leaves the heart? And you have some choices. All of these are in units of acceleration, meters per square second. Well, since the blood was at rest, the initial velocity in the x direction, v sub 0x, is 0. We also know that the final velocity in the x direction is going to be 0.8 meters per second, and the length of time involved in going from 0 to that speed is 250 milliseconds. So the average acceleration in the x direction is the delta v in the x direction over delta t. Delta t was 250 milliseconds, which is the same thing as 0.250 seconds, and this speed was 0.8 meters per second minus 0. So you see what I get is that this is going to be 3.2. This should say meters per second squared, but that is answer C. The reason it's meters per second squared is because you have second, and a second is second squared. So the correct answer for this one is C. Now in the same setting, we have another question. If the aorta has diameter d sub n, and it branches into two equally sized arteries with a combined area equal to that of the aorta, what is the diameter of one of the branches? Well, and here are your choices as answers. Assuming that the aorta and the arteries are circular in cross-sectional area, not a bad assumption, we can use the formula that A is equal to pi r squared. That's the area of a circle, and so that's going to be pi times, and the radius is half of the diameter, so this is half of the diameter whole squared. So if we let dn be the diameter of the aorta, and d sub b be the diameter of each branch, that stands for branch, then the area of the aorta is equal to the sum of the areas of the branches. And so if we are substituting in, we know that those two are equal. So that means that if I take, cancel out the common factors of pi and 1 over 4, I get that 2 dB squared is equal to d sub a squared. Thus, you can solve that. You can take the square root of both sides, and you can get that the, first you can divide by 2 and then take the square root, but the diameter of the branches is equal to the diameter of the aorta divided by the square root of 2. That means the correct answer is B. Again, in the same configuration, if the velocity of blood in the aorta can be measured directly using ultrasound techniques, and it can, and we will talk about how we do that with Doppler ultrasound later in the course. So a typical graph of blood velocity as a function of time during a single heartbeat is shown here. So it starts, it goes much faster, then it slows down, and it goes back to rest. Which is the best interpretation of the graph. So you see here you have the blood velocity, and here you have time. The blood flow changes direction at about 0.25 seconds. The speed of blood flow begins to decrease at about 0.1 seconds. The acceleration of the blood is greatest in magnitude at about 0.25 seconds, and the acceleration of the blood is greatest in magnitude at about 0.1 second. Well, this shows the graph. So at 0.25 seconds, the blood flow does not change direction. It's always positive. The velocity is always positive, so it's always moving in the same direction. And in fact, it increases over the initial quarter second interval, so it does not decrease at 0.10 seconds. The acceleration is the slope of the curve, and we can see that that's magnitude of the slope is greatest near 10 seconds. It's almost going straight up, which means that the magnitude of blood acceleration is greatest at 0.10 seconds. So the correct answer is D. Now quickly, the three LSAs then. We will have LSA, I call it physics 0, having to do with vectors. So here I have three vectors, and as you know, displacement is a vector. So given these three displacement vectors, find the resultant vector, magnitude, and direction. LSA P1, now the second physics LSA. If a brass washer has an outside diameter of 4.5 centimeters with a hole of diameter 1.25 centimeters and is 1.5 millimeters thick, and here's the picture, and we know the density of brass is 86,000 kilometers per cubic meter. So if you put this washer on a laboratory balance, what will it weigh in grams? So you want to find the mass of this in grams. That is your problem. And here is LSA physics number 2, but it's the third problem. This is called the egg drop. You're on the roof of a physics building of your school that is 46 meters above the ground. Your physics professor, shown here, is 1.8 meters tall, is walking alongside the building at a constant speed of 1.2 meters per second. If you wish to drop an egg on his head, where should the professor be when you release the egg, assuming that the egg encounters no appreciable air resistance drag? So this is a free fall problem. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of each other and yourself. We're all in this together. God bless you all.